We're now going to prove the fact that when we have a four-dimensional function that has level surfaces in R3, the gradient vector, del f, will be a three-dimensional vector that's perpendicular to a tangent plane of a level surface. And since that gradient vector is perpendicular to the tangent plane, it can be used as the vector that is needed to find the equation of the tangent plane. So let's begin our proof. Let's let this three-dimensional surface be a level surface for some four-dimensional function. Now let's take this level surface and we're going to slice it with a plane in some arbitrary direction. And when we slice our surface with this plane, we get an intersection curve C. And let's say that this intersection curve can be represented by the vector function x as a function of the parameter t, y as a function of the parameter t, and z as a function of the parameter t. Let's also consider a specific ordered triple on this curve C that happens at time t naught. So this ordered triple would be x evaluated at t naught, y evaluated at t naught, and z evaluated at t naught. Let's recall that a vector in the direction of a tangent line to our curve C at this point can be determined by looking at the first derivative of that vector function evaluated at t naught. So a tangent line to this curve at that point would have a vector in the direction that is r prime evaluated at t naught. Let's also recall that the tangent plane to the surface at our point will contain all of the tangent lines at our point. Not just this one tangent line that we have, but all of them. So certainly our tangent line is contained in the tangent plane, which means that this r prime vector is in the tangent plane. Let's let our surface be a level surface of the four-dimensional function when the range element w is equal to some constant k. In other words, our surface equation can be rewritten as f at x, y, z has an output that is this k constant value. Now, let's differentiate both sides of this equation with respect to the parameter t. Since k is a constant, this right-hand side is just going to be 0. But we're going to need to use our custom chain rule tree in order to determine the derivative of the left-hand side. So let's remember, f, the 4D function, depended on x, y, and z, and each of x, y, and z, those values were parametric equations that depended on t. So to get this derivative of the left-hand side, we're going to go down the first branch, which yields a partial of f with respect to x, and then down this x branch to the t, we have a straight d derivative, dx dt. Plus, now heading down the y branch, we get first partial of f with respect to y. Continuing down the y branch to t, we get the straight d derivative of y with respect to t. Then we head down the z branch and get first partial of f with respect to z, times, continuing down the z branch, we get straight d derivative dz dt. Now let's write this as the dot product between two vectors. And those vectors would be partial f respect x, partial f respect y, partial f respect z, dot straight dx dt, dy dt, dz dt. Now let's rewrite each of these in a more compact notation. Let's use f sub x, f sub y, f sub z, and instead of dx dt, let's call that x prime t, y prime t, and z prime t. From here it's a little easier to see that this is the gradient vector for that four-dimensional function, and we're dot producting that with this that is essentially r prime at t. So what this tells us, we'll say therefore that gradient vector, since the dot product of gradient and r prime is 0, that means that gradient and r prime are perpendicular. But since r prime at t is a vector in the tangent plane, that means the gradient vector must also then be perpendicular to the tangent plane.